Section 4.3, Spanning Sets. If W is a vector in a vector space V, then W is said to be a linear combination of the vectors v1, v2 through vr in V if W can be expressed in the form W equals k1v1 plus k2v2 and so on through krvr, where k1, k2 through kr are scalars. These scalars are called the coefficients of the linear combination. So essentially we're saying that if you can build a vector out of other vectors by scaling those vectors and adding them together to combine to make that new vector, W, then W is a linear combination of the other vectors. If S equals W1, W2 through WR is a non-empty set of vectors in a vector space V, then the set W of all possible linear combinations of the vectors in S is a subspace of V. The set W in part A is the smallest subspace of V that contains all of the vectors in S in the sense that any other subspace that contains those vectors contains W. So we're saying that if we have a whole bunch of linear combinations of vectors in our set, W is a set of all of those, then combining them all together gives us an actual subspace. So we have to check that it meets the subspace criteria in order to prove this, and we also have to check that it actually is the smallest subspace in the sense that any other subspace would contain this subspace. So to prove this, how about we let W be the set of all possible linear combinations of the vectors in S. We must show that W is closed under addition and scalar multiplication. To prove the closure under addition, how about we let W equal C1W1 plus C2W2 and so on through CRWR, and V equal K1W1 plus K2W2 and so on through KRWR. So we're basically taking just two arbitrary vectors in W. Let's look at what their sum is. So if we take U plus V, remember that's just the sum of some linear combination of all the W's and some other linear combination of all the W's, then we'll add up the two different constants for each of the coefficients, and we'll end up with a linear combination of the vectors in S. Similarly, if A is any scalar, then A times U would be A times, well, U is C1W1, so C1W1, and then C2W2, and so on. We just multiply A through all those, which again is a linear combination of the vectors in S. So either way, adding and scalar multiplying vectors in S will still produce vectors in S. They don't escape. It's closed under addition, scalar multiplication, so by our subspace test, it's a subspace. To see that it's the smallest one, let W prime be any subspace of V that contains all the vectors in S. Since W prime is closed under addition and scalar multiplication, it contains all linear combinations of the vectors in S and hence contains W. The subspace W in this theorem is called the subspace of V spanned by S. The vectors W1, W2 through WR in S are said to span W if we write W equals the span of W1 through WR, or W equals span S if that set is denoted by S. As an example, how about we show that the standard unit vectors span Rn? So what we'll do is we'll write out our standard unit vectors, E1, which remember is 1, 0, 0, and so on, and E2 is 0, 1, 0, 0, and so on, and En is just 0, 0, 0, and the last entry is 1. Okay, so then let's take a vector V. We'll call that V1, V2 through Vn, and we'll write that as a linear combination of all of the standard basis vectors. So V1 multiplied by E1, and V2 multiplied by E2, and so on until Vn multiplies by En. So notice that's pretty much, that shows it, because any possible vector I have, I just have to take the first component and multiply it by the first standard basis vector, the second component by the second standard basis vector, the zeros will make it so that there's no contribution from anything else, so all I'll end up with is just the v1, the v2, and so on. And then there you go, I have v for any v. Notice this is the same as when we had I, j, and k. We wrote stuff in terms of I, j, k, where I was 1, 0, 0, j was 0, 1, 0, and k was 0, 0, 1. If we had v equal to, say, a, b, c, then that was the same as a times 1, 0, 0, plus b times 0, 1, 0, plus c times 0, 0, 1, and that was just ai plus bj plus ck. If v is a non-zero vector in R2 or R3 that has its initial point at the origin, what is a geometric description of the span of v? So how about we draw R3 really quick. So here's x, here's y, and here's z. And I'll call this vector v. Then if I want, I could scale it up. For example, over here it could be kv. Could also scale it any amount in this direction, and I could also multiply by a negative to get any amount in this direction. So it shouldn't surprise us that this line, if I could draw it a little bit better maybe, this line is the span of v. It's all the different possibilities that I can get from scalar multiplying it, or adding different pieces of v's. I'm never going to escape the line if I just span a single vector. So that's the line through the origin determined by v. So what if we had two different vectors? So in that case, you're not just adding the same vector over and over again, you're adding a vector in a potentially different direction. So in that case, let's take a look at what R3 looks like. So I'll draw, let's say, some little v1 over here. And I'll draw some little v2 over here. Then, if I want, I can scalar multiply this guy. So let's say that's, for example, k1 times v1. And then scalar multiply this guy, and I'll get k2 times v2. So if I add up these vectors together, I could use the parallelogram rule. I'll get some vector over here like this. That's, well, maybe a little bit straighter would be nice. That's k1 v1 plus k2 v2. And I could keep doing this to build vectors all along like that. So it shouldn't be too surprising that the entire plane is the span of v1, v2. So it's the plane through the origin determined by v1 and v2. How about we show that the polynomials 1x, x squared through xn span the vector space Pn? So I could just write a polynomial P equal a0 plus a1x and so on through an xn, and that'll be a linear combination of 1x, x squared, etc. through xn. So Pn is equal to the span of 1x, x squared through xn. Just by definition of what a polynomial is, it's just going to automatically be a linear combination of all of those guys. How about we consider the vectors 1, 2, minus 1 and 6, 4, 2 in R3. Let's show that W equals 9, 2, 7 is a linear combination of U and V, and that W prime equals 4 minus 1, 8 is not a linear combination of U and V. So how about we start with W. We'll set that equal to K1 U plus K2 V. We need to just figure out what K1 and K2 are. So remember, W is 9, 2, 7. So we have to write that as K1 times what U is, which is 1, 2, minus 1, plus K2 times what V is, which is 6, 4, 2. So distributing the K1 and K2, we get K1 plus 6K2 for the first component, then 2K1 plus 4K2, and then minus K1 plus 2K2 for the last component. So this gives us K1 plus 6K2 is equal to 9. And two more equations similarly, so I'll write those out. K1 plus 6K2 equals 9. We'll also get 2K1 plus 4K2 equals 2 by equating the second component. And we'll get minus K1 plus 2K2 equals 7. And what we can do is, how about we take this equation, add it to this one, and we'll get that 8K2 is equal to 16. So that means that K2 is equal to 2. And then we could just go and plug that back in. We can see K1 plus 12 equals 9. So K1 is negative 3. Okay, cool. So that means that W should equal minus 3 times U plus 2 times V. So that's a linear combination of U and V that'll actually make W equal there. To show that W prime is not a linear combination, how about we assume that it is? So we'll set W prime equal to K1 times U plus K2 times V, and we'll show that this is impossible. So W prime is 4 minus 1, 8. We'll set that equal to K1 times 1, 2 minus 1 plus K2 times 6, 4, 2, and that equals K1 plus 6K2 when we distribute and collect the K1s and K2s. Oh, oops, I have to keep going. That's only my first entry. And then we have 2K1 plus 4K2 and minus K1 plus 2K2. So we'll end up with 3 equations again. We'll get K1 plus 6K2 equals 4. We'll get 2K1 plus 4K2 equals minus 1, and we'll get minus K1 plus 2K2 equals 8. So then we can solve this. Again, we could take the top equation, add it to the bottom one to get K2. You should see that K2 is 3 over 2, and then plugging that back in gives us that K1 is equal to minus 5. But then plugging in minus 5 over here gives minus 10, And then plugging in 3 over 2 over here gives 4 times 3 is 12, divided by 2 is 6. And negative 10 plus 6 is not negative 1. So this actually doesn't work as a solution. And in fact, this system is inconsistent. Because the system is inconsistent, there are no k's that'll actually make this thing a linear combination of u and v. So that's it. We've shown this non-linear combination by showing that a system that we got by resulting in a possibility of linear combination would be inconsistent. Next, let's determine whether the vectors v1, v2, and v3 span the vector space R3. So again, we'll assume that they do. We'll write that the vector b, is equal to b1, b2, b3, where b will be a linear combination of v1, v2, and v3. So b will be k1, v1, plus k2, v2, plus k3, v3. And the idea is that we can choose k1, k2, k3 to get any such b in R3, provided that v1, v2, and v3 actually do span R3. So let's replace b with b1, b2, and b3, and we'll put k1 times v1, which is 1, 1, 2, plus k2 times v2, which is 1, 0, 1, and k3 times v3, which is 2, 1, 3. So then we'll get b1, b2, b3 is equal to k1 times this thing distributed, then k2 times that. We'll group together all the first components. So we should get that the first component would be k1 plus k2 plus 2k3, just by reading them off. Right, k1 times 1, k2 times 1, 2 times k3, and then the second component will be k1 plus k3. There's no k2 because it's 0, and then last component is 2k1 plus k2 plus 3k3. Okay, so again we get some equations. We get k1 plus k2 plus 2k3. For our first component must equal our first component on the left, b1. You must also have that k1 plus k3 is equal to b2. And we must have that 2k1 plus k2 plus 3k3 has to equal b3. So that gives us the coefficient matrix 1, 1, 2, b1, 1, 0, 1, b2, 2, 1, 3, b3. Let's get the determinant of this guy. So that's 1, 1, 2, 1, 0, 1, 2, 1, 3. I'm only taking the determinant of the left part of the augmented matrix. So that's going to be 1 times 0 times 3 minus 1 times 1. So that's 1 times minus 1. And then minus 1 times 1 times 3 minus 2 times 1. So 1. And then plus 2 times the determinant of this guy. So plus 2 times 1, which is 0. The determinant is 0, so the matrix is inconsistent. Well, the matrix has determinant 0, so the system of equations is inconsistent by theorem 2.3.8 that we did previously. So that means that v1, v2, and v3 do not span R3. because if the matrix doesn't have solutions for b1, b2, b3, that means we can't build up all of the vectors of R3 from these three vectors. How about we determine whether the set S spans P2? So what we'll do is we'll take an arbitrary vector in P2, which is just a second degree polynomial. So we'll say that that could be a plus bx plus cx squared. And we'll write that polynomial as a linear combination of the vectors in S. So how about I make the first one W1, and I'll make the second one W2, and I'll make the third one W3. So I'm looking for constants K1, K2, and K3 that'll make P a linear combination of the W1, W2, and W3s. So I'll write P as what I set it equal to, as we did in the last example, a plus bx plus cx squared, and I'll set that equal to K1 times 1 plus x squared plus K2 times second one, which is minus 1 minus x, plus K3 times 2 plus 2x plus x squared. Again, I'll distribute everything so that I get a plus bx plus cx squared is equal to K1 minus K2 plus 2K3 plus K1 minus K2 plus 2K3 times x plus K1 plus K3 times x squared. This way I have some coefficient times r x to the 0, some coefficient times x to the 1, and some coefficient times x squared. And I'll end up with an augmented matrix of 1 minus 1, 2a, because 1 minus 1k2 plus 2k3 has to be equal to a. Then I'll get 1 minus 1, 2b, because I have 1k1 minus 1k2 plus 2k3 has to equal b, because the coefficient for x has to equal the coefficient for x. And then I'll get 1, 0, 1, c for 1, no k2, and then 1k3. And again, I will look at the determinant. So let's look at the determinant of 1, 1, 1, 1, minus 1, minus 1, 0, 2, 2, 1. And there are repeated rows here. So you can imagine adding one row to the other and getting a row of zeros. So this thing is going to equal 0 by theorem 2.2.5. So that means that this system is inconsistent. Again, by theorem 2.3.8. So that means that S does not span P2, similar to our last example. How about if we have the set x plus x squared, x minus x squared, 1 plus x, and 1 minus x? Then, again, let's write an arbitrary vector. So we'll say p equals a plus bx plus cx squared. And we'll write that p, we'll assume that p has to equal k1 w1 plus k2 w2 plus k3 w3 if this set actually does span P2. So we'll write a plus bx plus cx squared equals k1 times x plus x squared plus k2 times x minus x squared plus k3 times 1 plus x. And, oh, oops, I forgot that there's actually a k4. In this case, there's 4 vectors, so I need k4 w4. So this will actually be plus k4 times 1 minus x. And that means that a plus bx plus cx squared should equal k3 plus k4 for a constant term plus k1 plus k2 plus k3 minus k4 by grouping everything for our x term plus k1 minus k2 for our x squared term. So that'll give us the augmented matrix 0, 0, 1, 1a, because we have 1 k3, 1 k4 has to equal a. Then we get 1, 1, 1 minus 1b for our next term, and then we get 1 minus 1, 0, 0, c. So let's see if we can reduce this matrix to reduce our echelon form. So it looks like I could take this row and swap it with c. So how about I do that, and at the same time I'll take b and c and add them together, and that way I can get a 0 over here. So I'll end up with 2, 0, 1, minus 1, b plus c by moving this up and adding it to b. And I'll get 0, 2, 1, minus 1, b minus c by subtracting c from this row. That way I can get rid of that 1 over there. And a is in the bottom now, 0, 0, 1, 1, a, because I already have that 1 over there in a, so that's pretty convenient to have a on the bottom. The a row, I mean, on the bottom. Okay, so now all I gotta do is divide this by 2, divide that by 2, and I just have to get rid of these 1's over here. So I can just add minus a to both of these rows and divide by 2. So I'll do that. I'll get 1, 0, 0, 0, minus a plus b plus c divided by 2. I'll get 0, 1, 0, 0, minus a plus b plus minus c divided by 2. And I'll get 0, 0, 1, 1, a for my last row. Okay, so I was able to put this in reduced to echelon form. So that means that it is consistent for all a, b, and c. So no matter what a, b, and c is, you could solve the system of equations, you could find a linear combination. So voila, span of S actually is equal to P2. S does span P2. Pretty cool. So now we have a couple more examples to determine whether each of these sets spans M22 set of 2 by 2 matrices. So we'll start with A. We'll write a generic, or just a general arbitrary 2 by 2 matrix. So that could be A, B, C, D, and we'll set that equal to some linear combination of the matrices in S. So that'll be K1 times the first one, which is 1, 2, 0, 1, plus K2 times 1, 0, 0, 1, plus K3 times 1, 2, 1, 0, plus K4 times 1, 1, 1, 1, and let's see if we can actually find K1, K2, K3, and K4 that'll work. So notice this is the same thing as writing A, B, C, D equals, well, I'm going to distribute out the K1s and the K2s, etc., and add up all these matrices, and I'll end up with K1 plus K2 plus K3 plus K4 for my first entry, then K3 plus K4, and 2K1 plus 2K3 plus K4, and K1 plus K2 plus K4. So that should give me the augmented matrix 1, 1, 1, 1A for my first entry, and then 2, 0, 2, 1B, 0, 0, 0, or sorry, 0, 0, 1, 1C, because there's 1K3, 1K4, and then 1, 1, 0, 1D. Okay, so let's get the determinant of this. So the determinant would be the determinant of 1, 1, 1, 1, 2, 0, 2, 1, 0, 0, 1, 1, 1, 1, 0, 1. And that'll be equal to, let's see, I should probably expand along this third row. I've got 2 zeros over there. So I get 1 times this matrix that's built up out of all of these guys that 1 doesn't touch. So that's the matrix 1, 1, 1, 2, 0, 1, 1, 1, 1. And then I'll subtract this determinant, because remember it's plus, minus, going from left to right, and for that third row at least, and I'll get minus 1, 1, 1, 2, 0, 2, 1, 1, 0. So I just took basically this matrix. Okay, so then that'll give me, let's see, I'll expand along the second row again, because why not? In this case, second row, so this will be minus, plus, minus, so I'll get minus 2 times the determinant 1, 1, 1, 1, because it cuts out this, that's what I have left, and then minus, because this is plus and then minus again, so I don't have any contribution from 0, so then it's minus 1 times, again, determinant 1, 1, 1, 1, so that's for the first determinant, and then my second determinant be minus, I'll cofactor again along here, so minus 2 times determinant 1, 1, 1, 0, that was a little bit messy. Yeah, it's a little better. And I'll subtract minus 2 times 1, 1, 1, 1 to finish it off. Okay, so then notice this is 0, this is 0, this is 0, so all I get is everything comes from here. It just gives me minus 1, and this is 2, so I get minus 2. Okay, cool, so the determinant is non-zero. So the determinant non-zero means that this thing is consistent, so the span of S actually is M of 2, 2. Cool. Okay, let's do the next one. So again, we'll write an arbitrary matrix, A, B, C, D. We'll set that equal to K1 times 1, 0, 0, 0, because that's our first matrix in this example, plus K2 times minus 1, 0, 1, 0, plus K3 times 0, 0, 1, 0, plus K4 times 0, 1, minus 1, 1. And I'll get A, B, C, D equals K1 minus K2 by distributing the K's and adding everything up. K4 and K2 minus K3 minus K4, and then K4 again. Cool. So that'll give me the augmented matrix 1, minus 1, 0, 0, A, 0, 0, 0, 1, B, 0, 1, 1, minus 1, C, 0, 0, 0, 1, D, for the system that I would get from equating these guys. So then I'll get the determinant of the coefficients. So minus 1, minus 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, minus 1, and then 0, 0, 0, 1. Okay, notice I have a repeated row. So this determinant is 0. So that means that S does not span M22 in this case, because our system of equations is inconsistent for K1, K2, K3, K4. So let's end by saying that if S is equal to V1, V2 through VR, and S prime equals W1, W2 through WK are non-empty sets of vectors in a vector space, then the span of V1 through VR is equal to the span of W1 through WK if and only if each vector in S is a linear combination of those in S prime, and each vector in S prime is a linear combination of those in S. So we only have equivalent spans if you can write each of the vectors in the different spans in terms of the vectors in the other span.